As I said, I know I mentioned this as we were actually going through 5.5 with the substitution rule for integrals. As we move forward, and actually in these two examples, what you have to decide when you're evaluating an integral is if you need substitution or not. So not every integral needs substitution. Not every integral can use substitution to find it. So if you look at example 4, we have the integral of e to the x plus 1 over e to the x. First of all, what I want to ask you, what is this problem really, what is it really asking you to do? If I ask you to find an integral, what am I asking for, okay? Yes, an integral is an antiderivative. And then if it's a definite integral, it's the antiderivative evaluated on that interval. So e to the x plus 1 over e to the x. That expression, the way it's written, we do not just have an antiderivative for. The question is, do we need substitution for it? So if you were thinking, okay, I'm going to try substitution, what might you choose for u? So, okay, I heard e to the x plus 1. Okay, if you chose e to the x plus 1, so that would mean the top of this fraction would be u. So then what would du be? Just e to the x dx. Now, if I rewrote this, this is e to the x plus 1 times this e to the x on the bottom is not the same as this one. This is really 1 over e to the x dx. So this substitution, choosing e to the x plus 1 as your u, this does not work. Okay, so you could also reason if you just chose e to the x, so that would mean this is u. You're also not going to get rid of your whole top part. You'd have u plus 1. So substitution is not needed for this because I can actually rewrite this function as the integral of, when you have a fraction, you can split the numerator and have e to the x over e to the x plus 1 over e to the x. So I have just two separate fractions. And I know e to the x, well, I'll write it this way just so you can see where everything is coming from. I can split it, so it's that whole thing. But that means the e to the x over e to the x, that's just 1. And then 1 over e to the x, I'm actually going to write this as e to the negative x. Chain rule for a derivative, yes. So what you could do is you could split this into two different integrals. Not that you'd have to, but you could. I could split this and say I have the integral of 1 dx plus the integral of e to the negative x dx. Because what is the antiderivative of 1? X. Antiderivative of e to the negative x? It's what? It would be negative e to the negative x. Now that does come from, if you notice, in order to take the derivative of this, you would need chain rule. That means you really are using substitution. However, you could actually come up with this antiderivative without using the substitution rule. It is negative e to the negative x. But this is why, if I let u equal negative x, then du is negative 1 dx. And the negative 1, I this would become u. I have a dx. I don't have a -1. I would have to put the -1 in front. And I would have then -1 times the integral of e to the u du, which the antiderivative of e to the u is e to the u, so it'd be -1 e to the u, and then I would just put the -x back in. Okay, now, when you just have e to a power where there's a coefficient in front, sometimes you can reason through what the antiderivative is without having to do the substitution. Just make sure that you're checking if it actually works out. Sometimes, in this case, it may be easy to see what the antiderivative might be. So then it also is indefinite. So what do I need to include? Plus c. So x minus e to the -x plus c is the antiderivative, or the answer to that integral.
Are you impressed that I included that plus c?
Very.
I almost think like, no, I know this.
Yes, indefinite integrals need a plus c because it's just asking you for the antiderivative. Here now, if we have example 5, so it is the function, or it's the reciprocal of the function we just worked with. This one you cannot split the way we split the first one. You can split a numerator, you cannot split a denominator.
Can you substitute?
Does substitution work for this one? Yeah, if you look at the substitution we tried here, that would actually work here. If you chose u is e to the x plus 1.
Just let it be shown that I came up with that answer. That you could.
Du is e to the x dx, because this e to the x is in the numerator. Your denominator is u. So this would become the integral of e to the x dx is gone. That's the du. The denominator is u, so it's 1 over u du. So make sure that u that's in there is in the denominator, 1 over u.
Wow.
What is the antiderivative? Yep, natural log of the absolute value of u plus c. Then you put e to the x plus 1 back in. So natural log of the absolute value of e to the x plus 1 plus c. Morgan? So this, I could rewrite this as the integral of, if I kind of split this, I would have 1 over e to the x plus 1 times e to the x dx. So the e to the x plus 1 on the bottom is u, and then the du e to the x dx is just du then. Okay, any questions on those two? Okay. Then, 5.9 is the last section we cover in Chapter 5. And I know some of you were not here Friday, so I'll just remind you. In the past, I've included 5.9 with Chapter 6 just due to timing. That's really the only reason I've included it with Chapter 6. It does fit in with integration, so I'm including it here. That means the test on Chapter 5 is Thursday. So today we're covering 5.9. Tomorrow, Wednesday, just review.
What are we doing Friday?
Thursday, we'll cover something Friday. Yep. Yeah, Friday we'll cover something. We need to make sure we get through things before the AP test here. So 5.9, the nice thing is there's really one new thing in 5.9, and that's the trapezoidal rule, or finding a trapezoidal sum. The rest of 5.9 is review. We've already covered it. So this is all on approximate integration. What do you do when you can't find an exact value of an integral? So it gives two situations where it's impossible to find the exact value. One way would be if you are unable to find an antiderivative and you can't use substitution. The second way would be if you don't actually have a formula for f of x. Say you just have a table of data. There's no way to get an exact value of the integral. It's going to be an approximation. So we can approximate values of definite integrals using Riemann sums, which we've done already. So this is just a review. Riemann sums, remember, are using the left endpoints or the right endpoints. So I did include the sigma notation for it. But just remember, this is calculating the areas of all of the rectangles. So you would first figure out what is the width of each rectangle using delta x is b minus a all divided by n. And then based on your intervals, you would figure out if you're using left endpoint or right endpoint to find the heights of your rectangles, add all the areas together. So we've done that already. That was 5.1. Midpoint rule we've covered already as well. So you find your delta x, you find the midpoint of every interval, and use the values at the midpoint to find your heights. Add all of those rectangles together. Trapezoidal is what's new. So the trapezoidal rule, I'm also going to talk about it as just trapezoidal sums. So if you average the left endpoint and the right endpoint approximations together, so I'm showing you where the trapezoidal rule comes from. So this is kind of like a proof as to where this formula at the bottom, where it actually comes from. And I'm going to draw attention to, aside from this final way to write it, something in the middle that might be more helpful when you're working through certain examples. So we would say then the integral from a to b of f of x dx be approximately equal to the average of the left and the right endpoints would be half of their sum. So if we added L sub n plus R sub n and divided it in 2, that would be the average. But then what I'm going to fill in here are the sigma notations for both of those. And remember the difference between these. I'll just quickly talk about this here. So say your first interval is from x sub 0 to x sub 1. Once you find your delta x, this is your first interval. The left endpoint, all this says, if you plug in 1 for I, this means you're starting with f of x sub 0. You're starting with the left endpoint. Whereas for the right endpoint, if you substitute 1 in for I, you're starting with f of x sub 1. So that's really the only difference why they're written differently. But I'm going to substitute these both in. So we'd have 1/2 times, and then this just takes a little bit to write. So the left endpoint would be the sum from I equals 1 to n of f of x sub I minus 1 times delta x plus the right okay, so just filling those in. I had talked about this very briefly, and like I said, this is more of a proof. You're not asked to do proofs on your own. But properties of summations like this, we can rearrange this a little bit by properties. So because both of these, or rather I'll say this, I can write this as one summation, not two. So because both of them have multiplying by delta x with them, I can actually write that in front. So in front, I will have delta x divided by 2. So you can kind of see down in the final formula where that's coming from. And then what I'm left with inside is, because there's summations from the same interval of I values from I equals 1 to n, I can just write it this way as the summation from I equals 1 to n of the quantity f of x sub I minus 1 plus f of x sub I. This is supposed to be a final parenthesis at the end. So what I want you to notice, we're going to be going through an example too. I realize this might be confusing. What's happening is, say you have an interval. What's happening for every interval is you're adding the left endpoint function value plus the right endpoint function value, adding them together, dividing it by 2, multiplying that by delta x for every single one. So again, I'm showing you how they're getting from here to here. So then this goes on to delta x divided by 2 of, and I'm going to rewrite a few terms of this. So if I now substituted 1 in for I, this first one would be f of x sub 0 plus the second one would be f of x sub 1. So that would be the first interval. I would add f of x sub 0 plus f of x sub 1, really divide that by 2, multiply by delta x. But then plus what I would get then if I plugged in 2, so this would be the second interval, I would be adding f of x sub 1, 2 minus 1 is 1, plus f of x sub 2. So that would be the second interval, adding both of the endpoints together. And this would continue up to the last interval. So now this would be as if I substituted an n for the i's. So f of x sub n minus 1 plus f of x sub n. Sorry, that's hard to read. Let me squeeze that in there. But what I want you to see, because down here, notice in the final, they have some of the function values multiplied by 2. And this is why. Notice, now all of these are really just added together. But notice f of x sub 1 was the right endpoint in the first interval and the left endpoint in the second. So that's getting added together twice. And that would actually happen for all of the middle values. It would just not happen for f of x sub 0 or f of x sub n. So that's how they're getting from here to here, and why all of the middle function values get multiplied by 2. That's where that's coming from. F is the original function. So this would be if you're approximating it because you either can't find, or well, for some reason you can't find an antiderivative. Okay. Oh. That's kind of what this is showing, that if your delta x is constant for every interval, that you're kind of adding each one and then you're averaging the entire thing and multiplying by delta x. Is that what you were asking? Rather than dividing every one by 2?
Yeah.
Yep, and multiply by delta x. As long as your delta x is the same for every interval. So for some examples, which you'll see today, it's not. Okay, so now what I do want to stress though, I need your attention up here. What I do want to stress, don't memorize this. Okay, I know I can say that some of you still might. Don't memorize this.
Don't memorize it.
I'm going to show you an example of how to use it. Understand what it means. Don't memorize it. If you understand what it means, that means you can apply it to other examples. If you try to memorize this, this version of it does not work in every example. This version only works if all of your intervals have the same width of delta x, which in AP questions, they will not always give you intervals that have the same width, so that they prevent memorization, and they want you to show understanding. That's why. Okay, so I'm going to show you how to use it aside from memorizing what that looks like. Here's the reasoning behind it. Before, the left endpoint, right endpoint, midpoint approximations were all finding areas of rectangles. Areas of rectangles are length times width or base times height. So for all of these rectangles, the widths were delta x, and the heights were depending on if you had right, left, or midpoint, you substituted in a certain x value into your function to get your height. Here's the reasoning behind the trapezoidal approximations. What is actually being created are trapezoids, not rectangles. So I'm going to show here, this is kind of all for one function, what the rectangles look like for left, right, and midpoint, and then this is what trapezoidal looks like. So what it looks like is you take, graphically, you take the function value at each end, and you're just connecting them to make a trapezoid. It's not always an underestimate. It's an underestimate if the curve is concave down. If the curve is concave up, it'll be an overestimate. But trapezoidal is easier to see. Midpoint is the one that's hard to tell if it's under or over. Trapezoidal is easier to see if it's an over or underestimate, because either your trapezoids will fall under the curve, like in this one if it's concave down, or if it was concave up, you could picture the trapezoids are going to fall over the curve, and it would be an overestimate. Concave down is an underestimate, yes. Concave up, it would be an overestimate. But the reasoning behind this, I'm going to draw this trapezoid, but I'm going to turn it. Okay, so I'm drawing this trapezoid. I'm just rotating it so it's sideways, so it looks more like a trapezoid that you might be familiar with. This width is your delta x. And then this base, this length would be whatever f of x sub 0 is. This one would be whatever f of x sub 1 is. How do you find the area of a trapezoid?
You just guess 1/2. Take an estimate.
Okay, this is the area formula. I mean, there's different ways to write it, but it's half the sum of your bases times your height. So if you look at this, you have 1/2 times the sum of your bases would be your f of x sub 0 plus f of x sub 1 times your height is delta x. So that would be the area of your first trapezoid, and you would do that for every single one, but that is the reasoning behind that formula we came up with. Again, I don't recommend memorizing that formula that's on the bottom of the previous page. I included it. It's in your book. It only works if your delta x is equivalent for every interval, which it's not always on the AP test or in AP questions. So the way I'm actually going to work through example 1 or model to you is not using what's on the front.
I dig that.
Okay, so example 1. I did purposely put an integral on here that we could find the exact value of, because I also want to talk to you about error. So here's an integral we are going to approximate using both the trapezoidal rule and the midpoint rule. Trapezoidal rule, sometimes it's also phrased to use trapezoidal sums. So if you see trapezoidal sums, it means the same thing.
I don't know the trapezoidal rule.
Okay, first step is if we are approximating the integral from 1 to 2, here's our function. So f of x is 1 over x. It gives us n is 5. So still start out, find your delta x, find the width of each trapezoid, or rather it would be the height if you kind of lay it sideways like this, the height of each trapezoid if you want to think of it that way. So delta x would be 2 minus 1 over 5, so 1/5 or 0.2. Then I'm going to list out all the intervals I have. So we're starting with 1, so the first interval is from 1 to 1.2, and then so on.
Is
that really relevant right now? No, it's not. Once you have the intervals, here's how to start. So I'm going to say the integral from 1 to 2 of 1 over x dx is approximately equal to represent using trapezoidal, I would use t and then t sub 5 because our n value is 5. So again, I'm going to write this out more of a longhand way, not using exactly how it's written on the front, so you understand it. Understand it, don't memorize it. The first, or the area of the first trapezoid is going to be 1/2 times the sum of the two bases, which would be f of 1 plus f of 1.2 times your delta x, which is 0.2. Okay, so this is the area of just the first trapezoid. I'm writing the whole thing out. 1/2 times the sum of the two bases times the height. Plus, so this might be more to write out, but at least you understand where it's coming from. So plus 1/2 times, for the second interval, it would be f of 1.2 plus f of 1.4 times 0.2. Okay, now, hopefully you can see, because all of these have the same delta x, yes, it could be factored out in front. But that isn't the case if they all had different delta x's. If all of these intervals were a different width, that's often how it's given in the AP question, you would have to write it out this way. Plus the third one would be 1/2 times f of 1.4 plus f of 1.6 times 0.2. A plus 1/2 times f of 1.6 plus f of 1.8 times 0.2. Plus the last one, 1/2 times f of 1.8 plus f of 2 times 0.2. Okay, yes, this one is a lot to write out. Normally, so I do have on the back of this note sheet an AP question where one of the parts involves this. You're not always going to have 5 intervals, but I wanted you to see the longhand way. This is how it's written out. Any questions on that, how it's written out?
Maybe like a straight one.
Okay, now this would all, yes, you would need to calculate this just to save us some time now so that you can actually get to working on that AP question I have. So this would come out to be approximately, I rounded it to 6 decimal places on purpose, 0.695635. Because I actually want to compare these two approximations. Okay, so this just becomes now a calculation. I'm just saving us some time going through it. That's what it comes out to be. Okay, AP test, you just have to round to 3. I'm going to be making a comparison between these two, which is why I rounded to 6. No.
He was looking for that shortcut. Oh! It's gotta be somewhere.
Well, I mean, this one you actually have the function. Most of the time when you use this, you'll have like a table. Okay, midpoint rule. So this is the new part. I want to make a comparison though between trapezoidal and midpoint. So midpoint rule, just to compare these, go through how to set this up. You have the same delta x, you have the same intervals. However, you're calculating areas of rectangles and the heights fall at the midpoints of these intervals. So your integral from 1 to 2 of 1 over x dx would be approximately equal to the midpoint, m sub 5. Okay, so the first rectangle for the first interval would be f of your midpoint is 1.1 times your delta x is 0.2. So I'm writing all of these out longhand as well. This would be the area of the first rectangle using the midpoint, plus second rectangle would have an area of f of 1.3 times delta x is 0.2, plus the third rectangle f of 1.5 times 0.2, plus the fourth one f of 1.7 times 0.2, plus f of 1.9 times 0.2. Okay, just so you understand the setup again, this then just becomes a calculation. I have the value so that we can make some comparisons I want to get to. So this is 0.691908. Okay, so these are pretty close to one another. But now what I actually want to do is get the exact value. I want to talk about the error in these. Some of you I know had questions earlier on how do you know if the midpoint approximation is an over or an under estimate. To really know that, you need to know if the trapezoidal rule is an over or an under estimate. So trapezoidal helps you determine if midpoint is over or under, and you'll see why. How would you find for the integral from 1 to 2 of 1 over x dx? How would you find the exact value? Antiderivative, yes. So antiderivative of 1 over x is the natural log of the absolute value of x evaluated from 1 to 2. So it would be the natural log of, since 2 and 1 are already positive, natural log of 2 minus natural log of 1, which natural log of 1 is just 0. So I'm going to write this to 6 decimal places as well. Natural log of 2 is approximately 0.693147. Okay, so I know this is approximate as well, but this is the closest to the exact versus these two. They're all pretty close. Okay, are there any questions right now on the setups of either of these? I'm going to talk about the error, and then I'll be done talking. Okay. So, the error when you are finding an approximation, the error in the value of an integral is the amount that needs to be added to an approximation to make it exact. So if we have the integral from a to b of f of x dx, this would be equal to any approximation plus the error to that approximation. So that means the error, how to find the error for an approximation. If I solve this equation for the error, it would be the exact value, so the integral, the exact minus the approximation. Okay, so we're going to calculate the error that we found in the trapezoidal rule from the example we just did and the error in the midpoint rule. So I'm going to, for the error in the trapezoidal, I'm going to call this E sub t. So that error would be the exact value of the integral, which was the integral from 1 to 2 of 1 over x dx, minus the trapezoidal approximation t sub 5 that we found. So from the other side, since we rounded both to 6 decimal places, I'm just taking the 0.693147 and subtracting the 0.695635. So that error comes out to be a negative 0.002488. If the error is negative, this means it's an underestimate. And again, when you picture this, and I know I already said it, to draw in the trapezoids, you're connecting the two function values on an interval. So if the curve is concave down, it's going to be an underestimate. If it was concave up, it would be over, because your trapezoids would fall over the curve. So for this example, the trapezoidal estimate was an underestimate. The error in the midpoint would be the value of the integral from 1 to 2 minus what we approximated for the midpoint rule. So from the front side, that's the 0.693147 minus our midpoint approximation was 0.691908. So this comes out to be 0.001239. And since that error is positive, this means it's an overestimate. But it is closer. Okay, so here's what we can gather, what you need to gather from this. Do you have to calculate errors on the AP test? No. This is what I want you to gather from this, why I'm going through it. In some cases, you need to identify if the trapezoidal or the midpoint is an over or underestimate. What you should know is they are always opposite. The errors are always opposites. So trapezoidal is easier to see if it's going to be an under or an overestimate based on the concavity. If you know trapezoidal would be under, midpoint's an overestimate. If you know trapezoidal is an overestimate, you know midpoint's going to be an underestimate. They're always opposite. Just like left and right endpoint approximations are opposites. One's always over, one's under. Same thing with these two. And then another thing is, notice the midpoint approximation is actually closer to the exact. This error is about half the size of this one. Midpoint rule is always the best approximation. Now, you still need to know how to find all of them. You could be asked to find any one, right? Left, midpoint, or trapezoidal. Midpoint overall is the best approximation, though. So why they don't always just use it, I don't know. Don't ask me.
You got you close.
Maybe, but you wouldn't. Just don't do that. But maybe. I mean, when you average right and left, you get trapezoidal. So the trapezoidal is already the average of right and left. You'd be average, yeah, you'd have the average with another average. Okay, so here are a couple of things. One, I have a few practice problems listed, and I did Make a point for 24. Use the trapezoidal rule. I think in the directions it asks you to use something else. 25, use the midpoint rule. And then I do have, well, 24 is even, so that answer will be on Canvas anyway. 25, because I'm asking you to use something else, that answer will also be on Canvas because your answer using midpoint will be different from what's in the back if you do try that one. What I would recommend you work on now, what I included on the very back, and I will also include the answer to this on Canvas. Here is another AP question. You can answer the entire thing from where we are at this point. Every part of this. Now, one of these parts actually uses the trapezoidal that we just learned. The rest don't necessarily come from this chapter, but where we are now, you should be able to answer all 4 parts. So this is a free response question. You should be able to answer the entire thing. So I would at least make sure you work through this. This is some AP practice built in.
Like that.